Hey, it's Jason here, and I'm going to be talking this time about the nature of motion. We're looking at rotating reference frames. And why would we look at rotating reference frames in this video? Well, first, we're going to try to get at this concept because somebody on the channel asked about, do something about Lagrange points. And I thought, okay, Lagrange points are pretty interesting. They have to do with rotating reference frames. But also, we can look at the Foucault pendulum, and that helps us understand rotating reference frames. It'll also give us a chance to start to understand the Kerr metric for black holes. But the important thing is that we can use rotating reference frame to help us understand that the Earth is actually a sphere rotating on its axis and moving through space. And that's where we eventually get to with the Foucault pendulum. There's a lot of things that we have from rotating reference frames, including the reason that hurricanes rotate the way they do, the Coriolis effect that happens on Earth, as well as centripetal forces and centrifugal forces. One of those is real, one of those is not. So what we mean by real forces and fictitious forces, we'll cover all that. And we'll even discuss what we mean by an inertial reference frame, which is very important. So in order to get rotating reference frames, we have to do a review of Newton's laws. So let's start off with Newton's first law. Newton's first law says that there is this thing called inertia. And inertia is basically if nothing is acting on a piece of matter or mass, then what it will do is it will either stay at rest or continue moving in a straight line without speeding up or slowing down. So that's the concept and idea of inertia, and in fact that defines what we mean by an inertial reference frame. An inertial reference frame surrounds with a piece of matter, a grid of rulers going every which way, meaning 90 degrees forward, backwards, up, down, left, and right, as well as a stack of clocks all around it. That is called an inertial reference frame, and you can think of it as centered on the mass you're talking about. That's a good way of talking about it. Now, an inertial reference frame will follow the mass if it's at rest, or if it's moving in a constant speed or constant velocity in one direction. And that is the nature of inertia. We can define inertia with this P arrow equals mv arrow. That's another thing that's the momentum. And this momentum is what's going to change with the second law of motion. So the definition of a force is something that causes a mass to accelerate. An acceleration can either be a change of speed, it can be a change of direction, or it can be both. And an acceleration is a change in the rate of speed. You know what I mean? So we have velocity. Velocity is speed in one direction or in a direction, and if it changes either magnitude or direction, then you have an acceleration. So we can write the second law of motion either as F equals ma or F equals dp dt, which is the momentum, the change in momentum with time. So the dp dt version allows us to use like the rocket equation and some other thing where we would lose mass and so forth and so on. But we're not looking at that this time. We just want to make you aware that the second law of motion can also apply to changes in mass. For this example, we're keeping masses constant, and we're seeing what happens when a mass moves or accelerates or decelerates. So, third law of motion by Newton is that any object that exerts a force on another object, that other object exerts an equal and opposite force back on it. So for every action, there's an equal and opposite reaction, and all forces come in pairs. This is very important. All true forces, all actual forces come in pairs. And so that is an important thing to make sure we understand and keep in mind, because forces are things that cause mass to move. Anything that causes mass to move in a weird way that doesn't have an equal and opposite reaction might not actually be what we call a force. And we're going to get to that. That's what the purpose of looking at rotating reference frames is all about. But in an inertial reference frame, there's always an equal and opposite reaction. Anyway, So let's look at some second laws. Let's make it really simple. So here is an acceleration. For every second it goes up, it goes 10 meters per second faster. That's another way of looking at it. And then if there must be an acceleration, if we start by going the direction of the red arrow, going down at 10 meters per second, and we end up going to the right at 10 meters per second, the speed hasn't changed, but the direction has. So there must have been an acceleration, meaning we stopped moving down and started moving right. So that meant that there was a change in the velocity. So for the third law, we can always look at this is kind of a funny thing. The ball's not moving on the table. It's at rest on the table. However, it's being acted on by the force of gravity. And the table is pushing up on the ball with exactly the same amount of force that gravity is pulling the ball down. So therefore, the ball's at rest on the table. That's interesting to think, because people don't tend to think, oh, it's a ball on the table, there's no forces acting on it. That is not true. The table is pushing back against the ball. Now, if this were out in space, like what this slide seems to make it appear like it is, floating in space, if they happen to be in contact, that means they're totally at rest with respect to each other, and then there would be no forces. But I'm making this example on the surface of the Earth, such that the green arrow down is due to gravity, and the green arrow up is due to the force of the table. If we were to move this table to, say, the surface of a neutron star, where the force of gravity is really strong, then the force pushing back by the table might not be enough, and the table might squash down. Again, for every action, there's an equal and opposite reaction. The force of gravity is reacted against by the table's forces pushing up. So now what happens if we take that whole thing example and the ball might be spinning, or the table is spinning, or the room containing the ball and the table is spinning? Does that actually change anything? And the answer is yes. That is called a rotating reference frame. And a rotating reference frame is really important to understand a huge number of things in astrophysics and celestial mechanics and all sorts of stuff. In fact, relativity relies on this as well. So we have to understand that rotating reference frames change how we do things. They don't change Newton's laws, but they do change how we interpret them. So let's now look at this disk. It's viewed edge on, and on the surface of this disk, it's like a platter or a plate or a record or something, and let's say there's some mass object at the tip of the purple arrow R, and that thing at the tip of the arrow is just where this mass lies, and it's rotating on the disk at that radius R away from the center, which is the arrow going up. And the arrow going up just says, oh, if we're going up, then we're going to go right, we're going to go clockwise around it as viewed from the top of the arrow. The omega is indicating that we are looking at a constant angular velocity. It could be variable. The angular velocity, meaning how fast it's going around, could change. It could also be changing direction. The direction of omega could change, and the speed of omega could change. But let's just keep this really, really simple and make omega not change direction or speed. We're just going to keep it simple for this example, because it's hard enough once you start adding in changes and things. So for a constant angular velocity around an axis, around the origin of this inertial frame. So now let's take our object, and we're going to take this, what's not an inertial frame, because now we're going to rotate it through the inertial frame. Okay, so here we go. The rotation, by now the R, the arrow R, is going to appear to go around in a circle like hands on a clock. That's what's going to happen. And so we can describe that by changing the dr dt, meaning dr dt is a way of saying a little change in the vector r with respect to time. And that's what we mean by that. The ratio of the change of the vector r with respect to time is equal to the angular velocity cross product with the radial vector. Now, that cross product simply means the right hand rule. So what we do is we curl, we think of our thumb, our right hand, thumb pointing up along the green arrow. Well, take our hand, right hand, let's put it this way. Yeah, our right hand, take our fingers, and hold them straight up. And then that will be the direction your fingers are pointing, not your thumb, your fingers are pointing, is the angular velocity. Now curl your right hand such that it bends towards the purple arrow R, and then you make a curl, and it curls around your thumb. Your thumb then points in the direction of the omega cross R. That is the cross product, and that's what we mean. That's why the direction of where they're going, or the change in the radial vector with respect to time, is that cross product. So that's how we define this thing. Now, again, these little arrows at the top means they're vectors, and they can change in both magnitude and direction. But we're gonna simplify this whole thing, but by making omega constant, so that we'll drop that little vector notation at the top of it very, very soon. So now we go look at, suppose now that we've had defined how we're going to use our non-inertial rotating reference frame, now let's have the object that's at the tip of that arrow move inside the rotating reference frame with some velocity, vector v. And we're going to use that v cat, the little tick mark, to denote things measured with respect to the moving reference frame. So if you're on the surface of the disk, it'll look like you're moving on the disk. Now, that's very important to say, because it could be constant in the disk, meaning you're just standing there and it's spinning around. Everything outside the disk is spinning, but you're not moving on the disk. Here we're saying there's some velocity, some speed of direction on the surface of the disk, and that's what the tick mark is indicating. So we're just adding that in to say that this is an additional thing that we can have happen on the non-inertial reference frame. This will be important very soon. So now we're going to define something very important. We have to define these derivatives, meaning how much we change a little quantity with respect to time. And that's what we mean by the d by dt, is d over dt. We're denoting some change in something with respect to time. And that's what these ratios are, a little bitty change in this thing compared to a little bitty change in some time derivative, in some time increment, and that we get in the two different reference frames. One is in the non-rotating reference frame, and one is in the rotating reference frame. The equation at the top of the screen, dr dt, is the change in the radial vector in the non-rotating reference frame, meaning off the disk. So if you're outside the disk, you use the dr dt on the left-hand side. And we're going to keep trying to collect the things that are on the non-rotating reference frame on the left-hand side of the equal sign, and the things that are associated with the rotating reference frame on the right-hand of the equal sign. So that's how we're going to try to divide these things up so that we understand which side of things we're on. And we're going to violate that a little bit, but we're going to try our best. So from the fact, we're going to say, since an object is stationary in the rotating reference frame, but it appears to be moving in the non-rotating reference frame, then that's a very strange thing to say. It says the change in something in the non-rotating frame is going to be different than the change in the rotating reference frame. So we can't make these two time derivatives the same thing. So that's where the real difference comes from, and that's where we drop down and look at the last equation at the bottom. We have now defined the change in the radial vector with respect to the time derivative on the rotating reference frame. That's how we've changed the vector. And so that's basically that we're not defining a new vector for the position, our arrow. We're saying the velocity means that we have to measure the rotation, the time derivative inside the rotating reference frame differently. And that's what the bottom reference frame, the bottom equation means. Okay, so let's rewrite this again with standard velocity notation. We got v, which is the velocity in the inertial reference frame on the left, and on the right we have the velocity in the non-inertial reference frame, plus this little extra term that's due to the rotation. So those two velocities would be the same if omega was 0. But if omega is not 0, then they change. And this is simply the relationship between them. And that thing on the right, the omega cross r, is just how we relate the two frames. That's all. That is difficult. That is the velocity transformation between the two frames. That's a very important thing. So now we've got these three equations, which are all exactly the same. They're just denoted slightly differently. The top one is exclusively in the format of the radial vector that is moving that is fixed on top of, initially, fixed on top inside the rotating reference frame, but it is not fixed in the non-rotating reference frame. And so we just see that if we look closely, all of these things are identical equations. So make sure, and we're going to use the top one now for a trick, because look at the top one. It has one common element, and that is the radial vector. So we're going to use that as a trick. So let's take that first equation and extract the radial vector, which is the same thing throughout all of them. And we're going to extract it, remove it, delete it, cut it, however you want to say. And then we're left with this funny looking thing at the bottom, which is what we call an operator. And so this operator is a tool that operates on vectors that shows how we transform one vector from one reference frame that is rotating into a reference frame that is non-rotating. The right-hand side is the non-rotating frame, is the rotating frame, and the left-hand side is the non-rotating frame. So we can apply this to any vector. So we're going to apply this very soon. So let's operate now. Using that operator, we're going to operate on the velocity equation. Why? Because if we take a change in time of velocity, we get an acceleration. So let's do that, and we get something that looks like this. So we've taken the operator, which are in the parentheses, the big tall parentheses, and we're operating on the velocity vector equation. So remember, we're keeping things on their correct sides. We're taking the left-hand side gets the left-hand side operator, and the right-hand side gets the right-hand side operator. And that's because we have to match our reference frames. So as we keep our reference frames matched, we'll be fine. But if we swap them around, we wouldn't be fine. That would be a stinker. It would be very unfriendly. We'd have to operate again or undo the operation. So yeah, you could mix these frames up, but eventually you'd have to come back to this in order to make it legible and usable. And we just want to remember why we're using these things. So left-hand side, we're going to try to keep it in a non-rotating frame. Right-hand side, rotating frame. So we're keeping things together. All right, so now let's multiply out the right-hand side and collect the terms, and we see something that looks like the last equation there. So the first thing is the change in velocity in the rotating frame with respect to the time measured in the rotating reference frame. That's easy enough. And then we have the omega cross the dr dt and omega cross v, and then omega cross r, which is kind of funky. But if you look closely, the middle two terms are the same thing. So we can collect them. We can then redefine the change in velocity with respect to time as acceleration. And that we can, if we say the acceleration equals dv dt, then we can say, wait a second, a tick vector is the acceleration in the rotating reference frame, and a vector is the acceleration in the non-rotating reference frame. So we have these now two terms on the right when we do an acceleration or a change in the velocity inside of the rotating reference frame. It looks kind of crazy now. Now we're getting very complicated. However, it can be explained pretty easily. So the first term, we'll get to it, but those are our two terms. And we now then remember that a equals dr dt squared, and that's the two, we're operating on the velocity vector twice. But If we multiply through by a mass, like a little m, a mass, and then we collect terms and put things on one side and put things on the other side, we can then say, wait a second, imagine that we're now sitting in the reference frame. So the left-hand side wasn't just an interesting place to put the non-rotating frame and the right-hand side to put the rotating reference frame. Now we're going to say that the left-hand side is the reference frame in which we are measuring things. So the left-hand side with this MA tick arrow is the place where we sit. Let's say we sit in the rotating reference frame. So then that's why I've rearranged the equation this way. Remember, this final equation says on the left-hand side, we are in the rotating reference frame. So a mass times an acceleration inside a rotating reference frame is equal to some real force that's causing some sort of acceleration minus these two terms, which the first one is the centrifugal force, and it's called a pseudo force, and the far right hand, the second minus term, is called the Coriolis force. Now, it's important to note that a mass times an acceleration is a force, but the only one that's actually real is the capital F. That's the Newtonian force from the first, second, and third laws that we defined before. The other two terms that we're subtracting off of the real force are actually forces that arise because, or they're pseudo forces or fictitious forces that arise because we are measuring inside of a rotating reference frame. This is really important because these things wouldn't be there. Like the omega's there. If they go to zero, then F equals ma, right? But if you're inside of a rotating reference frame when you do your measurements, you will always have these things. Now, sometimes they're really small, like really tiny, but sometimes they are very big. So like a centrifugal pseudo force might be, think of the fun house, right? So you go to a carnival and you're standing in this canister that looks like a ringed room, and they spin you round and round and round and faster, and your back is slammed up against the wall, and all of a sudden they drop the floor out from under you, and your feet are like you see 30 feet below you, but you're slammed up against the wall. Why? Because you're in a rotating reference frame. And because you're in a rotating reference frame, you feel this pseudo-centrifugal force. Is it pseudo really? No, you feel like you're being pushed out. But the true force is the thing that's causing you to move to the right. That is the thing that's actually there is a force that's pushing you around. It makes you feel like to your right, let's say the thing is rotating clockwise from above, something's forcing the rotation of it, and that's the force. There is no outward force. You are being accelerated around a curve. However, if you look across from you, you see everybody inside of this thing. You can move to the left, you can move to the right. Nobody appears to be moving, and you can see straight across. Now, if you tried to throw a ball across, it would veer because the ball would seem to be moving across across a tube. Now, you can't throw a ball straight across inside the tube. It will curve, and that's the Coriolis pseudoforce. So Coriolis pseudoforce is actually the thing that is responsible for for hurricanes, the directions they move, not bathtub drains. It's too small. It's too small an effect for bathtub drains, but it had to be taken into effect during the Second World War because artillery shells weren't hitting their targets. They were veering to the left or veering to the right, or as they were pointing north or south. And so they took that into account. Why do I call these pseudo forces or fictitious forces? They're actually real things. They're true things on the surface of the Earth. They're not fake effects. But why do we call them pseudo forces? The reason we call them pseudo forces is because they do not obey Newton's third law. They do not have a back reaction. They don't push against anything. They're the result of transforming from one reference frame to another. That's their reason for existing. So They're pseudo forces. They're only there because of change in reference frame, nothing else. So the term fictitious force sure sounds wrong, but they're real effects. But they're effects because of the change, because we live on a rotating reference frame. Now it takes energy in order to keep the things rotating. So ultimately, the omega comes from some force, right, or comes from some momentum, right? So if there's no change in the rotation, then there is an angular momentum for which that is conserved as well. But in order to spin something up, there had to be some sort of force in order to spin something up. But we're talking about a constant speed, a constant rotation, angular velocity, and really we should take those arrows off the omegas because we're pretending. However, when we want to talk about the Lagrange points, or when we wanted to talk about, say, a Foucault pendulum, then we do need those arrows on the omega because they can change with respect to latitude. We can change with respect to how fast something is spinning or slowing down. So the most important thing here is that we don't live in an inertial reference frame because the Earth is a sphere that's rotating on its axis and orbiting the sun. But more specifically, for the purposes of this, we're rotating on our axis. And so the Earth's rotation on its axis is the omega that we're talking about. And the omega we're talking about is the rotation of the Earth. But if you're on the surface of a sphere, then you have to take into account where you are, latitude and so forth. But that's why that's a vector. Anyway, so this is the transformation of Newton's laws into a rotating reference frame, where the rotation is simply due to a constant rotation. Now, Newton's laws of motion apply to this, but that's why we call those things pseudo forces or fictitious forces, because they're only the result of a rotating reference frame. And we'll use these things in the future when we talk about the Foucault pendulum and Lagrange points and so forth. So there you go.